Hello, everyone. Welcome to this Windows Azure Platform Security Essentials session. My name is Enrique Saggese, and I'm a Senior Security Consultant with Microsoft. And we will be talking today about the Windows Azure Platform and how it addresses the most frequent security concerns. When we are talking about the Windows Azure Platform, we are thinking about one of the main exponents of the platform as a service cloud model. When we speak about cloud computing, we are talking about utility-like computing, in which you can quickly provision and decommission applications on top of standardized services, and on which you can basically pay as you go. You do not need to pre-provision a platform to build everything that you might need to have in the future or size for the worst case scenario. You can just build your application and deploy it as you need, allocating more resources as needed without having to go through the procurement process or through the resource allocation process. You simply build your application, you indicate how many resources you need at the moment, and you enable those resources. So this is what we call also the pay-as-you-grow model. You can ramp up and ramp down your infrastructure as needed, and that gives you lots of flexibility. With this flexibility also comes cost savings, since you can just pay for what you need and what you use. And also you get significant flexibility, and you improve your time to market, since as soon as you have the application ready, you can very quickly deploy on the infrastructure that you need. With all these, there are very significant advantages to adopting a cloud-based model for your applications, and in particular, the platform as a service model that Azure provides provides a great balance between robustness, cost savings, security, and flexibility. With a platform as a service, you get a pre-built platform that contains all the building blocks for your applications, but on which you run your own code. And unlike an infrastructure as a service model, in which you have to provide your own core components, your own operating systems and storage methods or anything like that, this platform is built from the ground up to be a cloud-based service. There are no legacy components. There are no compromises on technologies that were designed to be run on premises. This is designed to be run in the cloud and for the cloud. So it provides the best of both worlds. You have a very massive infrastructure that you can exploit to use in your applications, but at the same time, you have something that is built and managed as a utility with the flexibility to run your own code and without all the risks involved in putting in the cloud things that weren't designed to be in the cloud. So with all these, we see that cloud computing has significant advantages. Now, one of the biggest concerns related to the cloud computing model is control, is loss of control. When you put something in the cloud, you are basically saying to a company, please manage this part for me. With an on-premises model, at each layer, you design and deploy everything that you want, and you're on your own. From the physical model in which you manage your own data centers to the network, from the cabling to the switches and the configurations, firewalls, etc., the host operating systems and hardware, the applications that you develop and you deploy, and the data, you control everything. Well, it's not exactly everything, because actually you are buying pre-built parts. You cannot guarantee that the service you buy or every single line, unless you are going to audit every single line of the code that you are going to be putting in production. You may be missing something, and there have been instances where these components can have shown security risks. But in general, you feel pretty on top of everything that you've deployed on an on-premises infrastructure. But when you move to a cloud-based model, you lose some level of control over some of these layers. Obviously, you lose the control over the physical layer of all the cloud-based components. You deploy an infrastructure on the cloud, and you actually don't even know where physically this is located. It is running in somebody else's data centers. These data centers are not controlled by you, and they follow practices that you do not define. The network is from the internet until the hosts. It's completely managed by the application or the infrastructure provider, so you again lose control of that. The hosts can be partially controlled by you because you can configure them, you can deploy some proprietary images, or you can customize them up to some point, but in a significant portion, they are managed by the infrastructure provider, by the cloud service provider. Same thing with applications, though with applications you control a more significant portion. You can upload your own code, you can develop it, audit it, and it follows your own practices. But there are some components on the servers that are developed, deployed, and managed by the cloud service provider. And with the data, you control most of it, but depending on your configuration, you might be relinquishing some level of control of the data to the cloud provider. So with control, or with loss of control, sometimes you have some perceived risks. For example, when you deploy servers in your own physical location, your own data centers, you know who's getting in and out. You know who they are, what they do. You can audit them and you can control them. Maybe you don't do that. Maybe you are taking some risk, but you know what the risks are. With a cloud-based provider, you in general are accepting that things are being done properly by the cloud service provider, and you don't know exactly everything that's going on. Maybe on those physical data centers, there are operators that you don't know. You don't know what practices they follow. You don't know how qualified they are. So you are accepting a level of risk. It is a perceived risk. It doesn't necessarily mean that it is risky, because you should choose your service provider based on the trust you have in them and how transparent operations are. But still, the main blocker for cloud deployments today, according to most analysts, is security. Not actual security risks, not actual security incidents that may have happened, but the fear about security, and that is strictly related to the loss of control. Customers are concerned about the location of the data. If you have some types of data that might be subject to regulations or maybe legal aspects, you may not want that data to be floating around the world in locations that you don't know. You want to know where your data is, to what jurisdictions it is related, and where it is managed. You don't want, for example, your sensitive national security information to be located in a data center that's out of your country and maybe in the hands of another country that obviously you can't control. Second concern is how secure is the platform. In general, it's well accepted that most cloud-based infrastructure is reasonably well managed. And given the economies of scale and the huge scales of these data centers, these practices, and these solutions, it can be expected that any cloud infrastructure is on average better managed than the average on-premises deployment. It won't make sense that it is otherwise, given the massive scale and the huge investments the cloud providers are making. But it's difficult to know if that is really true because you do not control the infrastructure. Cloud service provider might say, "Hey, we are secure. We follow the best practices," but unless you can audit them, you can see what they're doing, and they are very transparent about their infrastructure, their practices, and their processes. It is difficult to really trust what's going on in the cloud. Another concern, very common concern, is who can see my data? If you upload data and sensitive data to the cloud, there might be employees in that company that can see your data. You might be operating under the assumption that some competitors, under some circumstances, could see your data if they are sharing the same infrastructure. And that is a significant perceived risk. Companies do not like to lose control over the data, and knowing who and how can see that data is an important aspect of trusting cloud-based platform. Another related thing is how can you know that the data follows your expected rules? Maybe you are following some regulations, and these regulations say that your data needs to be managed in a certain way, that it needs to be operated, that it needs to be transferred in certain ways. How do you know that's happening that way if you do not control the data because it's out of your hands? So that's, again, a significant concern. And finally, one big security concern is what happens if things change? What happens if the context changes? For example, you are relying on a cloud service, and suddenly that company that's providing the service goes belly up, and it announces that it's no longer going to be providing that service. So what do you do with your data? What do you do with your application? Can you just pull back and bring your data back to on-premises? And more importantly, will you be able to bring that data and those services in a way that you can use and that is efficient to use? It is important to know how you could proceed if you decide to pull back. Maybe it's not that the company fails, maybe it's that the conditions change and you decide that this is no longer your desired approach. You want to move to another cloud provider, you want to move to on-premises, the cost structure no longer benefits you, so you may decide to go other way, and it's important to know that you have the flexibility to pull back as needed. So those are the main risks perceived in a cloud-based platform. And let's now analyze how those risks are addressed by Windows Azure and how each of the components in the platform helps you not only have a secure and robust solution, but also to be able to know that that is the case, to be able to actually control your data, your services, even though this is a cloud-based platform. Let's begin with a brief description of how Windows Azure operates. Windows Azure is a cloud computing platform. It's what we call platform as a service. In platform as a service, the provider, that is Microsoft, provides a certain set of resources, not just raw hardware, data center, or housing for your infrastructure, but full-blown active services, including computing services, hosts on which you can run your processes, storage that those processes can use or you can use from your on-premises services, the network and communications and management elements that allow you to control this infrastructure, and different types of services that this infrastructure can use. More specifically, the Windows Azure platform provides what we call the compute resources. Compute resources are basically Windows-like based services that can be used to run your code. And on these services, you basically deploy your custom code, your custom solution, and this code runs in the cloud for your users, such as a hosted web service. And this runs on a customized version of Windows, a special version of Windows that is designed to as a host for cloud-based compute processes. We also provide different types of storage for blobs, data tables, and relational data. And again, this is not just a file share. This is not just a traditional dark storage in which you drop whatever you want. This is managed storage with which provides certain types of services, access controls, and technologies for replicating data, etc. So you get a rich service, not just data storage, but rich data storage in which you can automate certain processes and in which you can control who can do what. Microsoft also provides the management components, and those management components decide, for example, who does what, how can it be done, which element connects to which element. And the nice thing about Windows Azure is that you define that via rules, and you do not have to hard code that kind of thing. You do not have to rely on proper configuration at the device level. This is all defined in policies that you apply to your own deployment, and these policies automatically control who can do what and how. This is implemented at different layers. One of them is the network layer. At the network layer, local host-based firewalls and external firewalls define which devices control or connect to which devices and over which protocols. And by default, nothing speaks to nothing, and you, via rules and high-level policies, define who can speak to what, and that provides you high assurances that your data is not going to be accessed in an illicit way. This is very important because you are sharing the Windows Azure platform with other customers. So other companies might be even sharing the same piece of hardware. By deploying the solution in this way and managing connectivity through policies, you can have a very clear view of who can access what, and you can avoid misconfigurations that could lead to information disclosure. Microsoft provides the SQL Azure solution and building block. I will be describing this later, but it's basically SQL Server-based or SQL Server code-based relational database that can provide access to traditionally stored and managed data, but with a managed twist and in a very controlled fashion. And this is an aspect that you will see in all components in the Windows Azure platform. When let's say that you went with a infrastructure as a service approach for cloud computing, you deploy your own SQL Server, you deploy your own Windows servers, and then you basically are putting in the cloud the same service that you have on premises. And that means that there are tons of things that you need to configure, to define via policies, to be careful about, because these are general purpose computing platforms, extremely flexible, but at the same time, it is risky to put them in the cloud because you are the one that has to ensure that everything is locked down and nothing is misconfigured. When you put something on SQL Azure or Windows Azure or any of these components that were designed for the cloud from the ground up, they can design, pre-configured, and deployed in a way that is absolutely minimalist and that does not have things that shouldn't be there in a cloud deployment. You do not get components that are not needed. You do not get configurations that are risky by default. You get something that is locked down on deployment, and that is basically reduced to the minimal components that are needed for this to operate in the cloud. Finally, you also have some services, high-level services, that decide how you integrate the cloud-based platform with your own on-premises access control and your on-premises computing resources. For example, you can define certain communications between an on-premises server with a cloud-based service, so you can integrate both in a hybrid model in which some of your computing resources are in your offices, some are in the cloud, and both work together in an effective way, but at the same time in a secure way, because you have a very fine control over which communications happen and how they happen, and they happen over an encrypted channel and in a very controlled way. And also, you have access control based on your own identity providers. You do not have to replicate accounts or define your own directory in the cloud. You use your own traditional directories to manage this platform. On top of this solution, on top of this whole platform, you can run your own code. And while this is a general purpose computing platform and you could in theory run any code that you want, the solution is designed to run certain types of managed code, preferably such as .NET Framework applications, Java, Python, and PHP that are better suited to cloud computing environment in which the more control you have over what the applications can do, the better. So let's drill down a little bit more in the architecture of the solution, and let's begin reviewing different security aspects. Windows Azure is composed of a mix of roles that are deployed on the Microsoft Azure data centers. These roles are all controlled by what we call the Fabric controller. The different roles as deployed are called the Fabric. Myriad of nodes running in a Microsoft data center and implementing these roles are what we call the Fabric. The Fabric controller decides who does what, and how they do it. The Fabric controller is responsible for quickly provisioning services as they are needed, shutting them down, recycling them, wiping any remaining data that was in them in a secure way, and basically providing the on-demand resources so your application can run under your control. There are three basic role types that you can deploy as compute resources in the Fabric. The web role is basically an IIS-7 and ASP.NET based web server. This web role is based on a highly customized version of Windows. It's not just a out-of-box Windows deployed in the cloud. It is a highly customized, dedicated, and a very specific version that is designed to run exclusively as a web service, and that can run basically any IIS-based application, but that is designed from the ground up to run this service. This web role can interact with any client on the internet as well, depending on your definitions, and you control who can do what, but basically it's communicated to the internet, and on this you deployed your front-end code. Then we have the worker role. The worker role is the second role that you can deploy in Azure, and again, this is a highly customized version of Windows, but it is dedicated to running backend code. In this layer, you basically define your business rules, your operational code that decides what to do with the data. And this is typically persistent code that's running on the back end. Finally, there is a third role, which is the VM role. The VM role is not an essential or core part of the Windows Azure platform. It is a component that's implemented to bring flexibility, especially during the transition to the cloud. And on this type of role, you can run your own virtual machines, which are based on a customized version of Windows Server. So you build your own VM, you configure it, you install the services that you want, you basically define a significant level of control of what is in this machine and what it does, and you then upload that VM to the cloud. Even though it is very flexible and more customized or hands-on version of the different roles, it is still managed by the AppFabric, by the Fabric controller. You upload it to the cloud, and then the Fabric controller will say when it's instantiated and where it's deployed. And you can define policies about it, but you do not have to bring these machines up or down. It is automatically done by the Fabric controller in Azure. So these three roles share the characteristic of these being customized versions of Windows. The web role and the worker role are highly customized. They are basically not out-of-the-box Windows. They are based on the Windows code base, and as such, they benefit from all the improvements in security over the last few years on Windows, and benefit from all the know-how. And they also enable you to quickly learn how to build these and deploy these applications on top of this platform. But they are highly locked down. They do not allow you to do anything that you want. They allow you to only implement basically safe behaviors and restrict the usage of unmanaged code, restrict the usage of highly privileged accounts, and they are designed to provide a safe computing experience. The VM role is more flexible, but at the same time, it presents more risk. Even though it doesn't allow you to upload any kind of drivers or things that might compromise the platform, it allows you to use your own code in them and to customize the operating system to your needs. So deploying the VM role presents slightly higher risks than using the predefined web role and worker role that are much more locked down. One important aspect is that the web role and the worker role are not persistent roles. When you deploy these and you bring them up, if after a while they are brought down or they are shut down or restarted to be replaced with other instances of the same roles, there is no persistent data in these services. This has a few implications. One of them is that you have to store your data somewhere else, and I'll talk about that later. But another one is that if for some reason one of these web roles or worker roles became corrupt or damaged, or somebody found a way to upload malicious code to these roles, this damage is not persisted. When the worker role or the web role is recycled, the machine is started from scratch again. So that is one advantage of the Azure model, in which there is a clear separation between data and computing resources, and computing resources are not persistent. Every time they are recycled, and that happens frequently, everything that was in these nodes go away. But that is done in a secure way, so you do not lose data, you do not lose status. All the status is stored somewhere else. It's stored in a backend data storage services. So you do not have to worry about this implying that you will lose data or users will see an interruption, but it's done in an effective way, so you do not see your you do not see risks from compromise of these systems extending over time. So we have multiple layers on this infrastructure. On each layer, Microsoft has implemented a significant number of defenses. This is a non-exhaustive list of the things that we do to protect your data and to protect your services when delivered on the cloud. At the data level, we have encryption for data storage, and one important aspect is that you control the encryption keys. These encryption keys are built on demand as needed for you for your applications, and you control these keys. You can recycle them or renew them whenever you want, and all data storage on tables or on blobs can be encrypted this way. All communications are encrypted or can be encrypted through SSL, and that's the recommendation. All data transfers should occur over traditional SSL, both within servers or between servers and on-premises servers or clients, or internet-based clients. At the application layer, you can run your code on what is called a partial trust environment. In a partial trust environment, you basically block access to non-native code. To native code or non.NET, non-managed code. So your applications basically run always as managed code. And this prevents certain types of low-level operations from being performed, and protects the platform from the code or potential errors in the code. For example, if the application has a design flaw, and that design flaw allows some sort of low-level access, .NET code should catch that and not allow this execution to go out of the sandbox and compromise the platform. Also, in this model, all of your code runs in low-level or low-privilege accounts. So that is a big differentiator with most on-premises deployment and infrastructure as a service deployment, where you will see a significant amount of code running as a system or as administrative privileges. In this model, all your code runs under low privilege accounts. And this is a very significant aspect, because both on-premises and in the cloud today, the vast majority of exploits, of security exploits, happen at the application level. If you look at the most well-known hacking statistics or defacement statistics or vulnerability reports, the vast majority of incidents happen at the application level, not at the core operating system, network, or other levels. So knowing that your applications are mandated to run in managed code and with low privileges, does a significant helps significantly avoiding these kind of incidents. At the host level, we are using the latest versions of Windows, but not just the plain full-blown Windows, but restricted, very limited, and low-footprint versions of these operating systems. And these platforms are virtualized and running isolated from each other through hypervisor-based virtualization. This means that each instance is isolated from each other, and that you do not see compromises from one host or one guest to another. Guests are untrusted. They cannot just affect each other, and they cannot communicate in unapproved ways with each other, and they cannot affect the hypervisor or the hosts. At the network level, all traffic between machines, both virtual machines and on-premises, virtual machines based on the cloud and machines that are on-premises or the clients, are all firewalled, both at the host level and at the network level. So communications are kind of double-checked. Every communication between two virtual machines has to go through these firewalls, and has to go through the host-based firewall that's running on the virtual machine, but also through, the guest-based firewall that's running on the virtual machine, but also a host firewall that controls what the different machines do. And since the machines are untrusted, all traffic is parsed at the high level, and this parsing ensures that there is nothing fishy going on between the virtual machines. No unauthorized traffic is allowed, and by default, everything is denied. You have to define who can speak to what, unlike the typical network where things are allowed and unless denied. This is more similar to a DMZ in which each machine is in its own DMZ, and you have to say which ports and which communications are allowed between each pair of machines. You don't need to do that on a host level. You don't need to do that on a per machine level. You do that through high-level policies that define which roles in which applications speak to which roles in which applications and which on-premise systems. But everything is controlled, and you do not allow things by default. Also, all network traffic is encrypted both through SSL and through VPN-like communications based on IPsec, and I will talk about that later. Finally, at the physical layer, we have some of the largest and best managed data centers in the world with significant layers of physical security. All of our data centers have passed ISO 27001 certification, and also SAS 70 Type 2 certification for auditability. So you not only know that we follow the best practices for data center management, but you can also audit how these processes are implemented, and you can get reports on both the operational level and the incidents that happen. So we try to be as transparent as possible in the implementation of the physical layer, because that is something where you clearly see a difference between your infrastructure and this managed infrastructure. You control your own data centers. You do not control Microsoft's, so you want to be able to see what's going on, how they are managed, and who accesses what in your infrastructure when running on a Microsoft data center. So let's talk a little bit more about the compute model. I mentioned before these the three roles: the web role, the worker role, and the VM role. These are all running on a Hyper-V based hypervisor. This means that these machines are abstracted from each other. They can share the same hardware. They run on virtual instances that can have 1, 2, 4, or 8 processors or cores virtualized on top of a larger machine. And these machines can get varying amounts of memory and storage, up to 14 gigabytes of RAM. But they are all abstracted and from the underlying hardware, and they are all abstracted and isolated from each other. There is also a host VM running on each hardware instance that controls what goes on that machine. And one important aspect of this is that the web role, worker role, and VM role are not trusted. They are treated as untrusted entities. Microsoft assumes that these different modules are potentially malicious, since we do not control the code that runs in them. When you upload the code there, you define your application. So we do not assume that code is secure. We treat every communication with these machines as potentially insecure, and we firewall, audit, and control everything that goes between these machines. Also, when one role has to speak with another role, for example, a web role code wants to speak with a worker role, we force that communication to logically go through the internet. It actually doesn't go out to the internet and back, but logically it is firewalled and routed just like it was going to the internet, to ensure that there is no horizontal traffic going on between machines that could bypass the rules. So this provides a significant amount of isolation. Also, it provides a very standardized set of machines. For example, you do not upload your own drivers in these machines. And this is important because drivers are a significant source of compromise in on-premises deployments. Drivers work at low level. If compromised, they can actually take over a whole machine, so they are a significant target for attacks. Knowing that these machines run a very restricted set of drivers based on highly standardized hardware means that the exposure surface is significantly reduced. So the virtual machine is the security boundary between machines, and again, the host OS and the Fabric controller are trusted components. Microsoft manages them. We deploy them, and they are highly standardized. There are no variations, no exceptions. They are basically a single image that controls what goes on at those layers. So these components are trusted by Microsoft, but the guest OSs and the agents that talk between these guest OSs and the host infrastructure are not trusted and are assumed to be potentially malicious. And this model ensures that we do not assume that everything is going well with these machines. And at the same time, this increases the chances that actually things are going to go well in these machines, because we prevent that one affected machine, one compromised machine, extends this compromise to other virtual machines and affects other roles in the same application by the same customer and in other applications in other customers. So it's very important that we do not trust the code in these machines, and we treat these as kind of black boxes that we parse every communication, and we firewall and control every communication between one of these machines and other machines in the infrastructure. Also, all communications are validated and authenticated through certificates, so we avoid rogue traffic and things such as man-in-the-middle attacks, impersonations, and other typical attacks that happen at the network layer. Every communication is not only encrypted and signed, but it's based on identity claims that I'm going to be describing later. I mentioned before that these worker roles, or these these compute roles, such as the worker role, the web role, and virtual machine, do not store persistent data. Well, in the case of the virtual machine, you could store some types of persistent data, but in the worker role and in the web role, you do not store any persistent data, and these machines can be recycled at any time, and your application will continue to run, because all data is stored somewhere else. It's stored in the storage, in the Windows Azure storage components. The Windows Azure storage components can provide different types of storage that go from storing blobs that you control and treat as entities inside your application, but for Azure are simply binary streams, or structured tables to which you can use certain APIs to manage the data inside them. And we also provide SQL Azure, which I'm going to be describing later. All these data is managed on a separate hardware, and it's completely virtualized and organized in storage accounts. In order to access a certain object in this storage system, you have to have the secret keys related to that storage system. So when you create an account for storage, you define the type of storage that you're going to be using, and you also create a secret key or a set of secret keys. And these secret keys are going to be used by your applications to access this storage. And that way you ensure that even if physical access was granted, which is not, other applications or users won't be able to access your data, because only those that host or manage these secret keys will be able to access this data. You can recycle your keys as you want, and you can have up to 2 simultaneous keys for access. So you can configure one key to access a certain storage unit, and then you create a new key, you assign the new key to the application, and then you decommission the old key, so your applications that were still using the old key while you deploy the new one will continue to access your data in a secure way. And at the same time, other applications and other users won't be able to touch this data. This is the most basic model in which you basically give the keys to your applications and the applications access the data in a plain way. But you can also use compute roles to actually do access controls and decide who can be granted access to this data. So you build an application and use the identity model that I'm going to be describing later to decide who can do what on the applications, and based on that, the applications will access data and present only certain types of data to the users. All access and all communication is can be encrypted through SSL and with certificates deployed by this infrastructure, and the communications between the servers and the clients can also be, or on-premises servers can also be encrypted through IPsec in IPv6, and I'm going to be talking about that later. One very important aspect of security is fault tolerance. You don't want somebody to be able to bring down your infrastructure, and even if it's not malicious, something failing and bringing down your service is considered a security event. So all data on Azure is replicated. When you store a file, a blob, or a table on Azure, it's replicated at least 3 times to separate nodes. So single or even dual failure of hardware cannot bring down your data. This is done automatically and transparently. You do not need to write your data multiple times. Of course, in some cases, you might still lose data. For example, if you delete a file via your application, it will be deleted from the 3 instances, because we simply replicate whatever you put on data to all the storage units. So some organizations may want to build their own replication platforms, and we provide the necessary APIs so you can either at the application level or via these components for replication, replicate data between different instances of applications in Azure, or between your Azure storage and your on-premises storage, both for separate management or operation, such as in the case where you want to have certain types of data being used by both on-premises and cloud-based storage, and you want to have separate instances of data for that, or for long-term archival, redundancy, backup, or whatever uses you want to build this for. You just get replicas of data and you deploy them on premises. So you have robust and fault-tolerant storage in the cloud, and you can also replicate to on-premises to protect your data from other types of events. But not all data is unstructured in Azure. You also have what's called SQL Azure. SQL Azure is a relational database that is based on the same code base for SQL Server, for the latest version of SQL Server, or 2008 at least. It's built in the same engine, it follows the same logic, uses the same language, and uses the same data structure. So it's very familiar to those that have been developing for SQL Server or other SQL-based relational databases. So SQL Azure is still not SQL Server. It is a customized, locked-down version of SQL Server that provides the necessary services while at the same time avoiding the risk of a general-purpose platform running in the cloud. SQL Azure uses T-SQL, it uses store procedures, views, indexes, and any SQL Server feature that your application may want to use. So it is very easy to port applications from on-premises SQL Server to SQL Azure. And this SQL Azure database is accessible through ADO.NET, ODBC, etc. So migration and movement between on-premises and the cloud are very easy to do. But the security model for SQL Azure and SQL Server are slightly different. In SQL Server, you have SQL, or what's called native authentication, and Windows integrated authentication. Windows Integrated Authentication is designed to enable client applications to automatically do single sign-on to databases, and so you can more easily control identities in the database. In the cloud, your clients are typically not going to be accessing the database directly. So the idea is that in SQL Azure, your application level components will be accessing this platform. So you can use SQL authentication to access this data. This simplifies the model, reduces the exposure surface, and makes authentication more explicit, avoiding some risks of having integrated authentication. The authorization model is exactly the same. You, just as in SQL Server, you create users and roles on each database and associate them to user logins. So you have easy migration story from SQL Server to SQL Azure, but the implementation is slightly different because you do not have Windows authentication in SQL Azure. In SQL Server, you have several roles such as server admin and security admin and DB creator, which are very powerful, very useful for provisioning SQL Server, but also very risky because you may see applications that require some of these roles granted on databases, but in general, in many cases, they are left there just because they were deployed that way, and those are significant risks for the robustness and security of the databases. In SQL Azure, you do not have server admin, security admin, and DB creator roles. You have, on the other hand, some custom roles such as login manager and DB manager roles, which are granted in the master DB, so you can easily port from applications that use those server roles, server admin roles, security admin, and DB creator, but in a more controlled way and with lower risks. You, on SQL Server and on SQL Azure, you use the same protocols. You use TDS and SSL to communicate between SQL and the hosts, so that doesn't change in SQL Azure. In SQL Server, you have the Windows firewall and IP blocking using the host firewall, and you can obviously have external firewalls. In SQL Azure, you have an embedded in SQL firewall that not only does IP blocking, but it uses the access model for the SQL Server database to decide who can do what. So you have a more tightly bound firewall controlling who can access and who can do what on the server. One limitation in SQL Azure is that you do not have today storage-based encryption. You do not have transparent data encryption at the database layer. So today, if you want to encrypt data to store in SQL Azure, you have to do that at the application level in the worker role. So that is one limitation today. That said, putting encryption in the worker role is not a big deal, and you can move your current applications to SQL Azure by just adding some code to your application to perform encryption and decryption on the fly as data is written and recovered. Just like unstructured storage, SQL Azure provides a replicated storage model in which there is an active database, and this active database is replicated to multiple replicas, which are called secondaries. If one database fails, one of the other replicas is activated and declare the primary database, and then replication goes on from there. So you get an automated replication that provides robust storage and that prevents the data from from being lost if one storage unit fails. It is completely automated and transparent to applications, and you can also take replicas through replication services that are being deployed into Azure. You can take replicas to your own on-premises deployments or storage units, but you get automated replication for your databases in the cloud without having to do anything about that. That, again, provides protection against hardware failures, data center moves, or things like that, and it's a very nice thing to have because it protects you against lots of types of failures. And again, you don't have to think about that. It's done automatically for you. One big issue with some cloud-based models is identity and access management, because since these things are running in the cloud and your users are running in your own directory, and your applications are running in your own directory on premises, how do you relate the two? Having authentication protocols going back and forth between the two will be too traffic intensive, present latencies, and slow down everything. So how do you integrate a server that's running in the data center somewhere in the world with your on-premises directory without impacting performance? And also, how do you your directory infrastructure? Because you may have Active Directory or you may have something else as your identity base. So how do you integrate that with Windows Azure without adding complexity to Windows Azure? And the response is in claim-based identity. Microsoft has been for a long time a big proponent of claim-based identity and federation models for identity. And Windows Azure supports standards-based claim-based authentication. With claim-based authentication, you use your own directory, whether that's Active Directory or other standards compliant directory, to authenticate your users and to build claims, assigned claims about these users. For example, one claim will be a signed document or signed token that says this user's name is John Smith and he's a member of the Application X Administrators Group. And that identity and those claims are basically put on a certificate and sent to Windows Azure, and Windows Azure can confirm the identity and the validity of the certificate and apply those claims as rights on the system. So you then assign rights to an application to John Smith or to the administrators of Application X, and when you apply that kind of rights, they will be applied to the users that present those claims. So the nice things about this is, first, you do not have to replicate identities. You do not have to create a secondary repository of identities. Everything is in-house. You have your own directory. You have Active Directory on premises. You don't have to change anything there. You only have to implement claim-based authentication via federation. You can deploy Active Directory federation services to do that, for example. And then you grant rights on your own application. So you do not have to deploy any directory. You do not have to even have Active Directory, because it may be other directory that supports the same standards, and most modern directories do support these standards. And you do not have to build complex integration between the directory and the Azure platform. You simply accept these claims and you use the access control system that is part of Windows Azure to define who can do what based on these claims, and you do not have to integrate with your directory or your authentication process. You can also provide both on-premises and cloud-based identity providers through federation and through claims-based authentication. For example, you can use Windows Live ID or Facebook identities to access these applications, and you can say this user based on this Facebook's identity can access this application, or this server that has that uses standards-based claim-based identities, such as those based on WS star or SAML tokens, can access this application without having to authenticate in the traditional sense. It's already been authenticated and it has the necessary claims, so it can connect to these services based on those claims, and you get the best of both worlds. You get a very fast, very dynamic and easy to implement identity, and at the same time, you do not have to replicate identities. You use what you already have or what the users already have. This is all implemented through what's called the Access Control Services, and we've just released Access Control Services 2.0, which allow granting access through to web applications, REST web services, and now for the first time SOAP web services. And all these accesses are based again on standards. So you are fully interoperable with WS Star Federation-based services, or SAML. You can use SAML tokens to authenticate to the infrastructure. You can grant rights based on claims that you define yourself. You don't have to use any dictionary of claims that we use. You can define your own claims and you can apply them to these services. So it's very easy to define access levels, rights to different services, and to control who can do what over these services. This is a key element of the Azure security model. All the rest is about robustness. It's about ensuring that things go as desired. But in this case, we are talking about easing the way in which you define who can do what over your platform, and this is an essential element, because this is where a significant number of errors occur by granting the wrong level of access to a service. For example, by forgetting about decommissioning some account with administrative rights, or assigning the wrong level of access to a certain user. The whole claims-based authentication and identity makes it much easier to have the proper configurations and the proper access levels to this infrastructure. Connectivity is equally important, because unless you can ensure that only the right devices can access the necessary services, you have significant risks. So Microsoft uses IPsec-based connectivity, similar to what we have in direct access services in on-premises deployment. We are using the same protocol to connect with Windows Azure, so you can define policies and high-level policies saying this group of servers can connect with this set of roles, and these users can access these machines. And you define that at a high level and avoid having to specify per machine, per firewall rules. And this provides very simple to define and highly scalable configurations. This applies to both on-premises and cloud-based resources. So you can define how different modules of your Azure infrastructure connect and how they connect to your on-premises resources, such as your client machines or on-premises services. We provide very strict service level agreements for all these services and these components. And you can learn more about this by going to microsoft.com/WindowsAzure/SLA. You have there the exact service level agreements that you can get for each of these components, but these are market leading service level agreements that ensure you that you can get what you want from Azure availability. One final aspect of this whole solution. This is all very nice, but if it's improperly developed, well, it's all worthless, because if it's full of bugs, everything that I just said is invalid. The whole Azure infrastructure is design based and developed based end-to-end on the security development lifecycle principles. So all the learnings that Microsoft has had over the last few years on security and all the process improvements that we've had are applied to these from the get-go. The whole infrastructure has been designed and developed by applying the security development lifecycle. There is no legacy code. There is no compromises here. Everything has been designed by implementing the proper processes, auditing controls, security reviews, and this all reduces significantly the number of vulnerabilities, and it significantly reduces the severity of these vulnerabilities that might be by applying multiple layers of controls. So you can rest assured that the infrastructure itself is designed and implemented in a robust way. Of course, you have to apply the same level of care to your own deployment, to your own development, because the code that you will run in there and the applications that you will run on Azure will also be will also be vectors for attacks. So you should be applying the security development lifecycle or similar secure development practices to your own deployments in Azure. I mentioned already data center security. We have very robust and audited and controlled infrastructure, and you can learn more about this by going to microsoft.com/Windows Azure, and you have these different certification levels and all the practices that we are applying. They are all very transparently published there, so you can see exactly what's going on in these data centers. Data centers are redundant, distributed across the world, and more importantly, you can define where your applications run. We provide a content distribution network that can automatically provide provision data, so it will be delivered from the closest location to users, but you can also define that you want this application to be provisioned in this region and not get out of that region, or you want it to run in these two data centers and not get to this country. So you have that level of control in case your regulations or your market calls for that. If you like the concept but you're not ready to move to the cloud, you can deploy your own Windows Azure appliance. You can implement the same level of controls based on an appliance that you can buy from certified hardware providers. You basically buy a box that includes all the software, and you assemble it in your own data center based on the same principles that we publish, and you can build your own private cloud based on Azure. And then when you're ready to move to the cloud, you just redeploy your applications to the cloud, to Microsoft hosted Azure, and you don't need to rewrite your applications. And conversely, if you one day decide to pull back from Azure for whatever the reason, you can move to a Windows Azure appliance on premises. Let's say that your data becomes so critical that you need to pull back. You can do that by moving to Windows Azure appliance. So to summarize, because we are over time and I need to close up, Azure provides a very solid platform based on both technology, processes, and people. And we have, well, I think I have discussed already how all these elements work together to provide a robust solution. The technology is designed from the ground up, best of breed. There is no legacy, and it has been applied SDL from scratch. The processes are consistently managed, audited, and there are multiple certifications that you can use to audit and control this solution. And the whole procurement and provisioning process are highly monitored, audited, and based on best practices. And people accessing this platform are using lowest privileges, highly audited, and have physical controls on the access to these premises and to these services. All the components are lowest attack surface. We haven't just deployed Windows there. We have deployed a low attack surface version of Windows for each component. We are using standards-based, claims-based identity management and access controls to simplify your access to infrastructure. We are using very strong isolation between the elements, both at the network level, the host level, the virtualization level. Everything is encrypted or can be encrypted, depending on your needs, and everything is audited and defined based on high-level policies, so you do not have to care about specific nodes talking to each other and defining individual ports. Everything is defined at the policy level, so you have a very easy to manage and deploy security controls. Storage is encrypted, communication is encrypted, and you also have redundancy, geographic distribution, and denial of service prevention characteristic in the platform to address geographic failure issues or policy-related issues that might imply that you don't want certain data to run in certain places. So all these and many more things that I didn't have time to cover work together to provide a very robust platform that provide best of breed security, and that is actually on par with the best on-premises deployments, alleviating the concerns that you may have in deploying your solutions to the cloud. So with this, I want to wrap up, and I want to thank you for staying this late. And I appreciate your time, and I hope that this was useful to you. For more information, you can go to the Windows Azure Services site. You can Microsoft.com/Windows Azure, or you can get a 30-day free account on Azure by going to the link below and using that promotion code. And you can get 30 days to try these and learn about these in a more hands-on way. So with that, I want to close and thank you for staying this late on this session, and I hope this was useful to you. Thank you and goodbye.